Then let's start, and let's see where we left. Okay, yeah, probably the most boring part uh, of our presentation. Uh, just to give you some information about myself. So as Eva said, that many of my colleagues joined AMC Bridge starting from the time they were students, and I did that as well. So I joined AMC Bridge at my last year at the university, and here we are. Currently, I'm here with AMC Bridge for more than 14 years. Um, Growing up from junior .NET developer to the technical project manager um, during this time. And I think, yeah, lots of interesting projects and technologies are still ahead. So yeah, I mainly work with 3D graphics, different CAD, CAM systems, 3D mathematics. Maybe I think for the last 5-6 years, I started working with simulation, uh, lots of analytic geometries, 3D geometry algorithms, something like that. So yeah, I think then you know who's me, and let's start. So let's start with today's agenda. So during our meetup, we are going to learn who and what are the industrial robots. What does it mean? What is the idea and why we need to simulate them, and what it actually means to simulate the robot. We will learn what the main logic parts of the simulation exist, and go a little bit deeper into the details. So let's go. And now here's a question. So what do you imagine when you hear the term the industrial robots? Maybe you think about something like this, or maybe like this, but I must disappoint you. We're going to talk about some boring industrial robots that are normally employed and can be seen on the different factories or warehouses where they can help to replace the human or help the human to perform the work where we need uh, the highest accuracy of the work. Moreover, not all tasks can be performed by the human because, for example, something is too heavy to carry by the human being, or it's a very monotonous work that needs lots of efforts. So again, that's a place where we can think about applying industrial robot. So now I want to take a step back and just give you the insight how it all began. So the first industrial robot actually was invented in 1937 by Canadian researcher Taylor. It happened in Toronto. Of course, at that time, as you can imagine, industrial robot was very primitive. In fact, it was something like this, the crane, automated crane. And the only task it could perform, just move some wooden blocks for point A to point B. That's it. So the next important date is 1954. This is the year when two American researchers, George Devil and Joe Engelberg, they patented the first industrial robot, which was called Unimates. 2 years later, they formed their own company, Unimation, and this company later was bought, I think, maybe 10 years later, it was bought by Kawasaki company, Japanese company. So the next yeah, important date here is 1969. That's the date when the first robotic arm was released. And actually, was released to the public and was already on the market. And since the late 70s, we have a really robotic boom in the world. So many countries in Europe, America enter the market and are trying to develop something. At the same time, lots of Japanese companies started their researches. And yeah, there's one interesting fact that only a few non-Japanese companies actually survived on the market. There are different reasons why that happened, but yeah, there are few non-Japanese robot producers at the moment in the world. Okay, so I think then we can go next, but before that, just one more interesting fact. I really love to learn the new languages, and probably if you are interested in that, the origin of the word robot comes from the Czech language and can be translated to English as work or labor. And here's the question: how this word actually penetrated into all other languages? Because in every language, robot is robot. And that happened actually because Czech writer Karel Čapek wrote a novel. It was sci-fi novel dedicated to some human-like robots, machines, and he called that machine Robot. So that novel was very popular. Lots of theater plays were set and based on that novel, and that's how this word actually became so popular. And now we have it almost in every language in the world. So that's it about the history. And now let's see how the industrial robots looks like. So what it actually means to set up an industrial robot on the factory and what they can do. So at this video, you can see industrial robots produced by the Japanese company Fanuc, Fuji Automatic Numerical Control company. And this is the factory located in Hungary, which is famous for absolutely automatic line of producing Audi cars. So here you can see that industrial robots, they can perform different operations, carrying some heavy things, they can apply sealant, they can drill something, they can paint, or anything else. So that's the idea. That's what we are using the industrial robots for. Okay, and yeah, here we've seen some possible areas where we can apply and to use industrial robots. So let's understand what they can do. As I said, they can paint, they can assemble different things, they can weld, they can pick and place different objects, which is actually one of the most popular operations for the industrial robot. They can package, put some labels. Yeah, one more, I think, interesting area where we can apply the robots is cash handling. I'm not sure if you knew that, but like almost all big banks or companies that need to handle like lots of amount of cash money, they actually are using industrial robots to do that, to calculate, to move the pallets with money and all that stuff. Maybe it's more secure to do that with industrial robots than with human. So one more thing that industrial robots are used for is palletizing and product inspection, different types of testing, For example, I have a friend who works in the warehouse in Amazon, and he said that they have industrial robots, mobile industrial robots, who can move the pallets with some goods around the warehouse. So they have even special like robotics unit who can control, program these robots. They actually orient on a special net that is painted and painted on the floor, so the robot can navigate and understand where it is. Yeah, so that's the areas of application, the industrial robots. And now let's understand why we need to simulate them. What is the idea? What does it mean to simulate the robot? So, what is the robot simulator? Robot simulator software, that's an application to try and perform a real set, a real scene that we want to set up, for example, at our factory. But before we launch, before we put any expensive devices, robots itself are very expensive, and before we actually involve some people into that work, we need to make sure that that's safe, that we won't crash any expensive things around, and yeah, just to make sure that everything should go well, and that will help us to save time and cost. As you can imagine, before, maybe in 70s or even earlier, the simulation was performed using the real machines. And just just imagine when we think that, okay, now everything is ready, we've set up everything, we have very, very expensive things, and everything should work well, and then something goes really wrong. I think that's a common thing that happened to everyone. So the computer technology development and expansion made it absolutely clear that we should move this testing to the virtual space, to the virtual area. And here is the need that we need to develop a robot simulator software to do that. And even the first attempts of developing such software, they showed just absolutely drastically reducing time, cost, and danger of using the actual industrial robots. Yep, so this is why we need to simulate that. And yeah, as I said, when we think that everything should go well and no problems should arise, something goes wrong. Okay, now we know why we need to simulate that, and let's take a closer look what actually are the main components of the robot simulator and what we need to implement to create such software. So the main components that we can name are, of course, 3D modeling and rendering, because we need to somehow visualize what we're going to simulate, so our robots and scene and the process. Of course, we need to simulate movement. This part will include such ADS as robot controller, forward inverse kinematics, collision detection, but that's something that we will discuss a little bit later. Teaching, because we need to teach our robot, and yeah, again, later I'll show you what does it mean. And 3D vision systems. Actually, again, we will talk about that a little bit later, but you can think about it as an eyes of the robot. So the system that allows the robot to understand the environment. Okay, so ideally, if we developed such software, at the end we will receive something like that. So we can visualize the whole scene, the whole, for example, factory line, where we have conveyor, we have different work items, we have our robot that can perform different operations. For example, here we pick and place objects from the conveyor line to the basket. Here we can also see the 3D vision. So that's the camera that is placed above the conveyor and helps the robot to recognize where the work item is. And yeah, so that's basically the idea of what we are going to achieve at the end. Okay, then let's go a little bit deeper into the details. So to start the development of the robot simulation software, we need to decide how we are going to describe our robot. And for that, we need to think about some format that will help us to describe, for example, we're talking about the robot arm, one of the most popular industrial robots. So this robot arm will actually present it as a kinematic chain which has joints. For joints, we can think about joints. We can think as about rigid body, solid body. So it's solid body with 6 degrees of freedom. We also need to know such term as joint. And this is how the links of the robot are connected between each other. So of course, as you can imagine, here we have different options. We can have rotation, we can have just linear joint type, maybe move along some axis. It could be fixed or any combination of that. For robotic arm, we also need to know very important term, the end effector, and yeah, namely the TCP or tool center point, which gives us the idea. Actually, that's an axis at the end of our end effector, which help us to understand how our end effector is oriented in the space. So that's the idea. And yeah, as I said, TCP will help us to do that. So for the end effector, that's actually some useful tool that we have at the end of the robotic arm. And this tool, in general, we can split into, let's say, 2 areas. Something that can pick and place objects, move objects around, or some tools that can perform some actions. For example, welding or painting or drilling, grinders or something like that. So that's about action that can be performed by the end effector. And what about the object movement? We can also have different options here. We can have something that will grab an item, some vacuum cups, some magnetic grippers, hooks, scoops, and many other options that we can think of as for end effector. And that's actually the thing that does the work. So that's important to understand where it is located and how it is working and what operation it can perform. So what commands we can give to the end effector. Okay, I think this is clear about what can be at the end of our robotic arm. Then let's understand how to describe such robotic arm. I think it is clear that our format that we need needs to be able to describe robots, different robot types, also devices, work items. Of course, it has to have hierarchical structure because, as you can imagine, the robotic arm, the links, they are independency between each other. So if actually the parent link is moving, that means that all other child links will move in space as well. So we need to be able to set up and describe what joint type we have between the links. And yeah, there are different approaches how we can describe the robot model and the scene, but probably in most cases, we will come up with something similar to one of the, I would say, most popular formats at the moment, URDF, Universal Robot Description Format. This is a unified specification for robot, which is very simple. It has just, I think, known for everyone, XML markup format. It can be parsed easily using different programming languages. It's also used in ROS. ROS is Robotic Operation System, also a very popular thing. You can read about that if you are interested in robotics. So yeah, and let's see how it looks like. So to describe our links, actually, what is the link? As I said, for the link, we use the idea, the model of the rigid body. We also need to take into account such thing as such physical descriptions of the rigid body as inertia, some visual and collision features. So we need to set mass, origin to understand how our link located and where it is located in the space. Inertia, geometry itself, material, color, texture for the visualization, material for describing the physical characteristics of the link. And for joint, we need to set up type of the joint. So it could be, as I said, slide, fixed, rotate, or some combinations. We can set up limits. For example, we can say that, okay, this link has rotational type of joint, and it can rotate only from 0 to 90 degrees. That's the limit of this link, of this joint. So we also need to set up an hierarchical structure. So we need to mention who is the parent, who is the child, how to understand how these links are connected. An origin and axis. So, for example, to describe in URDF format the joint, we can have something like that. So we specified parent, child, origin, axis, so how this link can rotate, and velocity limits if we need that. Also some physical characteristics as friction and damping, and maybe some other things that are important to perform the physical simulation, which we're going to learn a little bit later. But anyway, as you can understand, the main idea of the simulation is to be as close as to the real world as we can. So, okay, now let's say we can describe our model. We can set up all the dependencies, describe the scene and work items that we have, and now we need to think how to visualize that. So for the visualization, usually we are using such formats as meshes or BREPs. I think the most popular formats for the geometry that is used in the modern rendering engines, and we need to select and choose what the rendering engine we are going to use. It could be OpenGL, it could be Blender, maybe some other implementations, it could be Hoops Visualize, or anything else. Actually, any graphical core might suit us. So here, yeah, on this table, you can see some of the robot simulator solutions and type of the 3D rendering engine they are using. As you can see, some of them use OpenGL, some have internal proprietary implementation of the rendering core. So it's actually always up to the developer to decide what we're going to use, depending on the format of the geometry and any other things or limitations that we have. Okay, let's move next. So what we learned so far is that we can actually describe the robot, describe the scene, describe the devices, and maybe work items that we have at our scene, and visualize that. So here we used, for example, Hoops Visualize 3D rendering engine to be able to parse the project file in that URDF format and load the geometry for the scene, for the device, for the robot surrounding, and for the robot itself, of course. So what we can do is to describe the robot, visualize that, and set up every player in the right place on the scene. Not a lot at the moment, but yeah, we can do more. So let's move next. Okay, but so as you can imagine, at the moment our robot is static and it's not interesting. We need to move the robot, and we want our robot to move something else, to perform some work for us. So for that, we need a robot controller. So you can think about the robot controller as a brain of the robot that actually controls all the motions, all the actions that robot can perform. If you're talking about software, then we will need to have something that we will call virtual robot controller. In real work, we have a mix of hardware and software solution, usually a box. Yeah, this is controller itself that will help us to manipulate the robot. If we are moving to the virtual world, we need a virtual robot controller. And with the robot controller, we will learn such important things, important terms for us as robot program. This is the program that can be run by our controller and will contain the instructions for our robot. And the second term is teaching pendant. Teaching pendant, that's again a hardware and in real world and software solution that will help us to teach the robot to be in the proper position. To create such thing, we will have to implement something that usually is called a digital twin. So a digital twin of that real controller, but in our virtual space. And of course, we need to integrate that with our software that we already created with 3D rendering engine and the parser of the project. Okay, let's move on. And here I want to give you an idea how the robot program looks like. Normally, it's very simple. It just has a sequence of addresses, and for each address, we save the position of the robot. Optionally, we can save the instruction. For example, instruction for the gripper can be release or grab the object. The robot program also contains the operation sequence to understand which is the next step that we should move to. And the teaching pendant that you were able actually to see at this photo as well. That's the manipulator that helps us to teach the robot to be in the proper position. Usually that looks like this or something similar. And this is a device that helps us to control this 6 degree of freedom of our end effector and be sure that our robot is in proper position. So basically, just a manipulator that helps us to send the robot to the proper position and record this position into the robot program under the specific address. Of course, we can control also lots of different parameters such as speed, maybe some preferable movement options, and so on. Yeah, one more interesting comment here is that every teaching pendant is equipped with that big red button. That's an emergency stop. And the teaching pendant as a device itself is implemented in the way that we can manipulate the robot, actually move the robot, only if the button is in the middle position. So if we press it too hard or if we unpress, release the button, it won't move. As you can imagine that the robot movement is very dangerous if people are around, and that was made for an additional security. Just an interesting fact. So let's move next. As I said, the teaching process is very important for the robot simulation software. This is the process where we can actually place the robot in the right position and save that to our program. In this moment, when we save that, we teach the robot two important things. The position, so we remember its end effector orientation, and procedure or action, grasp, release, or drill if we have drill at the end, or let's say paint something, if the idea of this robot is to paint, for example, the car. So then, for example, to have better understanding of the full robot program itself, we can consider this simple pick and place task performed by the robot, which is pretty straightforward, but as you can see, that still requires lots of additional details. So basically, almost all robots, they have some starting position or basic position. They also have, as you can see, the approaching position. Then we have an additional position actually that is used for the action, in our case for grasping. Then we have an escaping position and approaching position number 2, so to the place where we want to release the object. Then we have the releasing position itself, and at the end, escaping from the releasing position. So this simple pick and place program can look like that. As you can see, it contains also some instructions for the end effector, for the gripper in our case. And yeah, these programs, they are normally read and can be understood by our robot controller. So probably the next question from you is that, okay, if we save only the end effector position, how we understand how to move the robot? So how each chain in our kinematic, each link in our kinematic chain should rotate to reach that position. And for that, we should understand and get familiar with such algorithms that are very popular in the robotics. Namely, they are forward and inverse kinematics algorithms. So the idea of the forward kinematics is to find the position of the end effector by the given positions of the joint. So, for example, if we take a look at this simple planar problem, where we have a simple robot with 3 chains, so we know theta for each joint, and we need to find x, y, and c for the end effector to understand the position of the end effector. Of course, for this case, that's pretty easy, and we can solve that just using our geometry knowledge. But nothing is planar in our world, and for the special problem, we need to apply transformation matrices one by one to understand the orientation of the end effector. But that's the forward kinematics. And as you understand, the more popular choice is the inverse kinematic, which solves the opposite problem. So we have the position of the end effector, and from that, we want to understand how the joints should move to get into this position. So what are actually that theta angles for the joints that we need to set for the each link in the chain. So again, for the planar case, we can solve that easily and find theta 1 and theta 2 by knowing the end effector positions. But if we are talking about the special case again, and that's what we actually need to do, we will apply some numerical algorithms to calculate that. It's going to be iterative and approximate solution. Okay, so now we know how to calculate the robot's position, so how to understand how to move the robot. So at the moment, we can load our robot model, visualize that, in our case using hoops visualize, and finally we can teach the robot. So for example, we can put the robot in some position, in the desired position that we want our robot to come to, and say that, okay, that's the right position. I want to save this position under the specific address. For example, that's going to be this 2000. And then during simulation stage, we can ask the robot, okay, please go to the position 2000. And likely it's going to go to that position. Let's finish that thing. Okay, thank you, Robot. Okay, so let's move. Um, Here we were talking about the single point teaching, but in most cases we will have to deal with multi-point teaching. So we want to set a bunch of points and ask our robot to move through them. And for that, we need to actually plan the trajectory, taking into the account joint types. So if this is a rotation joint, it can only rotate. If this is linear, it can only slide or move linear. Of course, we also want to plan our trajectory to avoid the collisions. Otherwise, that's that's a not useful simulation. Again, we will probably want to optimize our path by different criteria. It could be distance, it could be time optimization to move faster from point to point, or it could be eco mode. So we want to save the power and we want to find the path that is the less power consuming. That's always possible. And the task is not easy. Also, we want to avoid the singularities. That's the situation when our robot can lose one of the degree of freedom. So for that, of course, we can develop our own algorithms, and that's great if we can do that, if we have time for that. Or we can try to use one of the existing libraries and packages for the motion planning. Just a few of them that can be found on the market are Robotics library. So this is C++ library for robot kinematics, motion planning, and lots of other things. OMPL, again, open motion planning library, but it doesn't have a built-in collision detection, which probably is not good because we definitely want to have some collision detection. Move it, and yeah, many other things actually can be found. So here, for example, we used the robotics library to be able to find the path between points that we want our robot to teach. So, for example, we can set up few points, and we really want our robot to go through each of that point. So here again, we are talking about the end effector. So they're setting the points for the end effector, for the TCP, where it should come. Then we can initialize the robotics library and pass all the geometry constraints, our joint types, and all other information that we need, and obtain the result. So the trajectory, the path for our robot. Yeah, in case we want to play that, it's going to look like this. Okay, good. Now we can teach our robot. But still, we are far from the idea of the simulation, because as I said, the idea of the simulation itself is to be as close to the real world as possible, to be able to really understand that what the scene, the operation that we simulate, they are close and or almost identical to what we will see in the real world, on the real factory, in the real warehouse, or whenever we want to set up our robots. So for the physical simulation, again, the idea of the physical simulation is to simulate, taking into the account all possible physical characteristics. So we need to take into account, of course, rigid body dynamics. We need to find the collision. We need to, again, if there is a soft body model that we use in our simulation, then we need to implement soft body dynamics or fluid dynamics. This is everything that is actually used in the real simulation projects. We need to, during the physical simulation, we need to estimate, for example, in our case, how the mass, how the friction, how the inertia is affecting our movement. Yeah, so here I think is interesting video that will show us why is that important. So in the first case, we have just nothing. And for example, if our robot releases an object, it just stays and is floating in the space, which is really not what is happening in the real world. At the second option, we don't have collision detection. Okay, we have gravity, but no collision, and you can see we are still far from the realistic description. For number 3, we don't have rigid body dynamics. So for this form, we understand that in real world, it's not going to slide because the mass, center of the mass is moved. And only the number 4, where we apply all these characteristics, looks like something that we might see in the real world. Okay, let's move on. Okay, for the physical simulation, we will probably, again, if you have an appropriate education and a few years of the free time, maybe less, we can try to describe and develop everything by ourselves. But in most cases, we will use some already physical engines. And the most popular at the current time are these options. So it could be ODE, a physical engine that is widely used in games and in 3D gaming. Probably you know some of these games. Bullet is also a very popular physical engine, mostly used for different animation and 3D graphics in films and cinema. Physics, that's more about simulation in CAD systems, in some university researchers or something like that. Vortex, that's also a very interesting one. It's not free and again is used for the academic projects used by militaries and in some other cases. Again, there are lots of options that you can find. It depends on your task, what exactly you want to simulate. Maybe you want something more lightweight and can find something that will fit and meet your requirements. Okay, so again, currently we can describe the robot, we can visualize that, we can teach the robot, we can plan the path, the trajectory for the robot movement, and we can simulate the real world behavior for the robot simulation for the robots. Good. Now I want us to take a closer look to one of the most, as I said, one of the most common tasks for the robots. Actually picking and placing some objects. It sounds easy from the first glance, but in fact, here's what we need behind that words and what really happens. So to implement the pick and place operation, we will have to think about and implement in our software such ideas and models as virtual camera model. So we need to implement and set up all the parameters we need to describe the virtual camera, field of view, actually position, clipping, the resolution of the camera, to be able to simulate that real camera image that we can see, for example, on this video, because that's a real camera and we are in the virtual world, so we need the virtual camera. We need to implement and integrate that camera with our software, because in the real world, again, that camera somehow gives the images and gives the data to the controller, which can process the images. And based on that image processing, the robot controller can understand, can recognize the objects in that image. Based on that recognized object, we can calculate the position for the robot that we need to send robot to actually grab or release, well, in our case, grab an object. So if you're talking about software, that means that we need to implement virtual camera. We need to implement and make sure that our camera communicates with the robot controller. We need to implement ray tracing algorithm, because we need to get an image. And in most cases, the most common approach for that task is to employ the ray tracing algorithms to receive a point cloud. And in this point cloud, actually in picture, we will need to make and run another algorithm. We need to find an object in that point cloud. And again, then based on that object position, we will calculate the robot's position. And we will send the instruction for the robot to go to that point and perform some action, grasp an object. So, yeah, that sounded very easy from the first look, but lots of details under the hood. So here at the video, we can see robot simulator software, which is called VREP. Actually, they have a student's version, so if you are interested, you can try and play with that. And here you can see how this virtual camera and pick and place objects idea is working. So the robots, they're using that virtual camera model to get an image, to recognize an object, and to get the instruction how to go to the proper position and grab that object. Okay, so I think we are going closer to the end, but a few more things before the end. I think based on what we've learned today, you might understand that the idea of the machine learning is actually might fit very well into some of the robot simulation software components, and that's really true. Especially machine learning is very popular for such tasks as motion planning. As you can imagine, we can train and use the historical data for the past motion planning to find the path faster and easier in the future. For the 3D vision system, again, there's lots of ideas where we can apply machine learning algorithms. First of all, we can try to improve object recognition and object classification based on the data we've got before. And yeah, we can faster receive the instruction for the robot to pick and get the proper object. Yeah, I think on the video you can see how manually you can teach the robot. So this is what is called reinforcement algorithms. I think actually after 15 times of that try, robot actually did that well. I think I've tried much more and still cannot get that. Okay, so this is good. I think you might think, okay, but why do we need to start from scratch and implement all those algorithms and components? Why I can just get one of those robot simulation software you were talking about at the beginning? That's a good question, and here is why. Industrial robots, they are extremely popular, and they are getting more and more popular each year. You might be surprised, but not all, and really, I would say less than majority of the robot producers, robot manufacturers have their own software. And as you can understand, if we are using some other third-party software for our special needs, we need to customize that, and everything can be customized to some limits. So sometimes the customization actually is more expensive and less effective than creating something from scratch. And yeah, as long as robots cannot survive without us, we still have a job. That's our good news. But I'm not sure about that because I think this video was published on Boston Dynamics Twitter just 5-7 days ago. And that's just incredible. I mean, what this human-like robot can do, definitely not all the people in the world can do such actions. I'm really amazed by the stability and all the work they've done. So yeah, the last point was probably needs to be reconsidered.